Hi there, this is Professor Myers, formerly Professor Gracie. Today we're going to be covering section 7.1 from the Larson text, which covers area of a region between two curves. This video is based on a guided notebook that I made. It's on my website if you want to print out the pages that relate to it. The website is www.mathchick.net. That's mathchick.net. All right, so here we go. We're going to be focusing on finding the area of a region between two curves using integration. So instead of just one curve and the x-axis, now we're going to be looking at what it would be to find the region in between two or more boundaries that are not necessarily just the x-axis. And we'll also be looking at integration as an accumulation process. So here we go. Let's check it out. Whoops, sorry. Whoops. Okay, so let's check out a let's go ahead and make the graph of two intersecting curves. So if we have, there's a few different things that are going on, and you just have to be real careful that you know exactly what you're looking at. So if we go to here, our calculator, so let's take a look at, suppose we had something like, I don't know, maybe 8 plus x and then minus 2x squared or something like that as one of our curves. And then suppose we had another curve that's just, let's just do x squared. Okay. And then let's also take a look at a simpler case where we have just a single graph. So let's say we have, I don't know, we could have, well, we could look at, this will be good. We'll look at these. Okay, so let's suppose that in this first one, we'll graph them both. And let's adjust that window to be where y is going. We'll try negative 10 to 10. Or actually, let's just zoom standard. There we go. And now we can set our window to be a little nicer. And then our y minimum, why don't we just have be negative 2? And we'll graph. There we go. All right, perfect. So let's take a look. We're going to copy this guy. Sorry, got the dogs going again. we're going to put this guy over here on the right because it's a kind of a more complicated case. And then we're going to go back to our graphing calculator. I'm going to go to the y equals, right? And then I'm going to keep the initial graph and we'll clear out this one. And we will see how that graph looks. Okay, and that's good. So now we'll copy this one. So here's a couple of different cases that we're going to explore. This first one, so we have a scale. We're going from -5 to 5 on the x-axis. This here is -2 to 10 on the y-axis. We'll just call this x, or y and x. And then same thing over here. -5. Down here was -2. And this is up at, actually, up here is at 10. So the 10 for this one would be up here. Okay, so basically what we have going on is, I'm afraid if I erase, I'll erase the whole graph. See? Okay, so this 10 is over here. All right, so, and this is, of course, y, and this is x. So our first graph that we had graphed was the blue graph, and the blue graph was, I think we did call it, we'll put it over here. So this is going like this, and this blue graph is f at x equals 8 plus x minus 2x squared, and that's the same thing over here. Minus 2x squared, and then the red one was just, call it g of x is equal to x squared, right? So on this one, what we are going to do is we are going to say that we are bounding this region between f, the graph of f, and on, we're going to go from the region between, we're going from the negative, basically x is -1 and x is 2. So the wording would be that we would be bounding the region on the left side between the graphs of f, x equals 1, x equals 2, and also in order for there to be a bound, we'd need also to have a bound of, you'll either see it as the line x equals 0, or you would see it as the y-axis. And we'll call this region 1. And so that your region You want to be able to draw these out and picture them. It's going to be especially important for the next section. But region 1, you're basically going to have the region that's bounded by these 4 graphs, right? So that's how it would look, and oftentimes they might just give you the bound on X. So in the problem, they might just say, oh, you know, find the area between the of the region bound by the y-axis, the graph of X, and then they would say from X going from -1 to 2, right, inclusive. So there's a couple different ways they can give you that region. All right, so basically in the red, this in the first graph, what this translates to is it gives us our limits of integration. So you basically have the integral, all right, and we end up having for this one, you take a look and you have this rectangle, right, a vertical rectangle, and it works similarly for when you have functions of y instead of functions of x. But this rectangle here represents the height of the region at a given interval. And here, this little piece right here, that represents the base of this area rectangle, right? But so this base of that rectangle, and that's your change in x, which equals our dx, okay? So in this case, our first graph, right, if we're looking up and down, our first graph is really going to be the blue graph because that's your topmost graph. So you always want to do your topmost minus bottommost, if that's even a word. And that gives you your height at that given interval times the change in x, which is your dx, and then your limits of integration, right? So if we call this here a and this b, you'd be going from a to b, okay? So in our picture, we have the integral from what to what? Good, -1 to 2. And then our topmost graph is what? Perfect. Our f of x, so that is 8 plus x minus 2x squared. And then our bottommost graph is perfect. The y-axis is the same as y equals 0, right? So minus 0 and then dx. And that gives you the area, for this given example, that gives you the area between curves, and where you have one of the quote-unquote curves is the y-axis, and then you're given an interval from x is -1 to x is 2. That gives you your bounds left and right, and your topmost bound is the graph of f. Okay? And then you would just complete the problem. Now, in a case like this, there's a little more going on. Okay? So, our region 2, it's completely bound by these two graphs. So you don't need any more information than what you're given here. So basically, what do you think you need to find? Beautiful. You need to find your intersection points, right? So here, call it A, and you can call this guy B. This ordered pair is going to be B, comma, the function f evaluated at B. And this ordered pair is going to be A, comma, the function evaluated at A. But what's really important is just finding A and B. So what you end up doing is to find your limits of integration, right? You solve the system of equations. So this one happens to be a nonlinear system of equations. You might have a curve and a line. You just never know. So here, you basically are going to set f of x equal to g of x and solving. Then you do the same thing, right? You do your bottommost minus your your topmost graph minus your bottommost graph. Then you'd get your limits of integration, and you'd go from there. So here, let's see what those limits of integration would be. So if we go back to our calculator, and actually we could probably just solve these by hand. I didn't really leave space for it. Let's go up here. So here we go. If we set f of x, which is 8 plus x, sorry, eight plus x minus 2x squared equal to x squared, that's setting f at x equal to g of x. I'm going to go ahead and get everything on the right side, so I'll have 0 on the left. I'll end up having, when I add, I'll have 3x squared minus x minus 8. Okay. Now this one, you'd need something that had a overall product of negative 24 and a difference of 1. So here you'd have to use the quadratic formula. So you'd end up with x is negative 1 plus or minus the square root of 1 minus 4 times 3 is 12 times negative 8 is going to be, I think, negative 96 all over 2a, which is 6. So we would get x is equal to 1 plus or minus root 97 over 6. So I don't know if that can be simplified or not, but what we would have found here is our limits of integration. So our limits of integration would have been negative, sorry, the screen's going wild here. Okay. Okay, so we would have negative 1 minus root 97. All of that is over 6, and the upper limit would be 1 plus root 97. Whoops, I did it wrong here. All over 6. I know they're weird looking limits of integration, but that's okay. And then our topmost graph is still f, which is 8 plus x minus 2x squared minus, now we have x squared as our bottommost graph, and then it's with respect to x. So those are kind of a couple of setups. Of course, you're going to find a ton of different situations, so you just got to make sure you make the sketch and figure it all out, and then use your integration techniques to find the area. Okay? All right, so let's check out this next part. Okay? So this next part, we're looking at, two functions that are continuous on some closed interval from a to b. And we're also assuming that the graph of g lies below the graph of f. So with this one, the area of the region between the graphs is literally, you kind of think of the complete area below the topmost graph, and then you're subtracting below the bottommost graph. So let's take a look at just a little visual here. Okay, so here we've got, let's say we've got our, that's crooked. Let's say we have y here, and we have our x-axis here. And suppose we have some curve, call it f, that looks like, suppose it looks like this. And suppose we have some other graph. Oh, let's name that. So this is our f at x. And then we have some other graph g, like this. That's our g at x. And let's suppose our a is about here, and our b is over here, and let's also suppose that we have some xi here, right? Now, our a hits the lower graph, the bottommost graph about here, and then our b hits our lowest graph about here. And if we take a look at xi, all right, what's happening is, do you see that about here is where the xi hits the graph of f? And so if we kind of go over here, this distance here is f at xi. And then if we look over here, this is where we hit, xi hits the graph of g at x. And so this distance here is g at xi. Now, over here, you end up with what's called, now you got to think of this as being magnified, but this is called the representative rectangle. And this distance here is the width of that rectangle, or the base, call it, of that rectangle, is our delta x. Let's highlight that. So this little bit is delta x. And then the height of our rectangle is here, right? And that is what? Measure. How could we figure that out? Beautiful. What you get here is you subtract f at xi, or actually you're subtracting g at xi from f at xi, and like we were talking about before, the topmost graph minus the bottommost graph. And if we look at our overall area for this, our region, so let's highlight that. This here is that distance. And if we look at our overall region, what we have is the region that's bound between A and B, and it's under the graph of F. So this here is the region that we're considering, okay? But the concept behind it is, hey, you know, if you kind of do hash marks, right? And if you say, okay, well, if I do this kind of notation for all of the area infinitely under the graph of F that's still bound between A and B, isn't it going to look like this? It would just go on and be bound, and it would go on forever unless you have something that is being subtracted out from it. So what we do then is we're subtracting out the bottommost graph area. So I'll highlight that. So the diagonal marks are the area under the curve of F. And then we can look at this region over here, and what color do I have for you? I don't want to do it too dark. Let's go here and find a color for us. Let's just do a light, kind of a peach color. So if you look at the region under, try again. If you look at the area under the graph of G, do you see it's all of this going on forever? And so it literally subtracts out, our f of x, the area under the graph of f at x. And then we end up only with the area between the two curves. So it's really pretty groovy. All right, so that's how it works out. Just kind of I thought a picture would be worth 1,000 words in this case. All right, so that area ends up being, you know, you basically take the area of all those infinitely many representative rectangles, right, and you sum them all up and evaluate the limit as the number of rectangles goes to infinity, and you end up with the formula given here. Okay, so let's go on to an example. Okay, so the first example has us finding the area bounded by the graphs of y equals x cubed, y equals 3x squared minus 2x, x is 0, and x is 2. All right, we have x cubed is our first one. And then the next one is 3x squared minus 2x. So 3 times x squared minus 2 times x. All right, so let's take a look at the graph. So here, I mean, can you see, it's pretty hard to see what's going on, and we're interested we're integrating from 0, x is 0 to x is 2. So really what we want to do is we want to figure out what's really happening there. So if we go to, you can go to something called Zoom Box. I'll do that. And it allows you to just box the area or the region that you're interested in. And we really want to go up high here so we kind of get a whole picture. And then you press enter where you want to start the corner of your box, and then you can push down or right to give you one of the edges of the box. And now we'll go to the right and it will make our box. I'm going to go just past X is 2 because that's what we're interested in. So here we go. Oh, and look what happens. Do you see how they switch? So let's do a further change here. Let's make our Y maximum smaller. No, do we want to do that? No, not really. Let's do our scale. Hang on a second, let's go back to the graph. Okay, so let's do this. No, we're good. Go back to our graph. Okay. So now this was really tricky because they cross at some point. So we are going to need to find the solutions to the nonlinear system of equations. So let's go ahead and copy this guy. This is from an earlier version. So what we're going to end up having are two regions, it looks like. So before we label them, let's go ahead and find the limits of integration. So finding the limits of integration, I guess I'll start up here, find limits of integration. Now keep in mind you've been given x is 0 and x is 2, but there's something in the middle that we have to find. Okay, so we'll just solve this system. We know for sure we've got these two, but we got to find the one in the middle and if there's any others. So to find the limits of integration, we set them equal to each other. Okay, I'll just start with y is x cubed, which was our blue graph, right? So that is y equals x cubed, and then our red graph is y equals 3x squared minus 2x. So if we set x cubed, and we're going to set it equal to 3x squared minus 2x, and solve that, let's see what happens. So we'll get x cubed minus 3x squared plus 2x equals 0. Factoring out an x, we'll have x squared minus 3x plus 2 is equal to 0. Factoring further, we will have x minus 2, x times x minus 2 times x minus 1 is 0. So see how we get 3. So we get x is going to be 0, x minus 2 is 0, or x minus 1 is 0. So you get x is equal to 0, 1, or 2 as your intersection points. All right? So let's check it out. So here is our first intersection point. At 1, we also have an intersection point, and at 2, we have a third intersection point. So now we need to look here and check it out. So what you'll see is that we have a region here, this little region here. Oops. This little region here gives us our first region that we need to contend with. And then we have this other region. I'll go ahead and do it in this purple color. So on the first region, which graph is on top? Good. So this is region 1. So region 1, and this here is region 2. So the blue graph is on top for region 1, and in region 2 it switches and the blue graph is on the bottom. So what's going to happen is our area, so next task is to find the area. So when we do that, let's see what we have. We're going to have the area is really equal to region 1 plus region 2. Okay, so far? So the blue region and the pink region. So let's define those areas, right? So the area region 1 is going to be the integral from, 0 to 1 of x cubed minus, with respect to x. And then region 2 is going to be, the integral, the integral from 1 to 2. And then now we'll have our 3x squared minus 2x first, and then we'll be subtracting from that x cubed with respect to x. So, putting it together, we will have, let's see what we get for these integrals. So, simplifying and then starting the area, we'll have our overall area will be equal to the integral from 0 to 1, and this will simplify to be x cubed minus 3x squared minus, a minus is plus, so we'll have plus 2x dx. And then we're going to add to that the integral from 1 to 2 of 3x squared minus 2x minus x cubed with respect to x. So this will get us for our first integral, we'll have 1/4 x squared minus x cubed, the 3's will divide out, plus x squared, the 2's will divide out, and that's evaluated from x is 0 to x is 1. We'll be adding to that x cubed minus x squared minus 1/4 x to the 4th. Oh, sorry, I missed I'm so sorry. This should have been x to the fourth. And that's going from x is 1 to x is 2. So, continuing, we'll have the area is 1/4 times 1 to the fourth minus 1 cubed plus 1 squared. And do you see that the lower limit is just going to be 0? And that is that first integral. Then the next integral will be two cubed minus 2 squared minus 1/4 times 2 to the fourth, and subtracting from that we'll have 1 cubed minus 1 squared minus 1/4 times 1 to the fourth. And continuing, we shall have, that'll be what these ones right here will zero out, so we'll end up with 1/4. And then on the next one we'll have plus 8 minus 4 minus 4, right? So I'll just write it out. So we'll have 8 minus 4 minus 4. And from that we'll subtract the ones. Do you see zero each other out? And then we'll end up with minus a negative quarter. And so at the end of the day, we will have an area of 2/4, which is 1/2 of a square unit. And we're done. Okay? So a lot of it is just, crunching through the integral. So basically, just so you can match it up, what we found was this was our region 2. And this right here gave us the region 2 area. And then this was our region 1. And this here gave us our region 1 area. Okay? So that's that. All right, so now this one here, we have 2 curves. All right? So with this one, we are going to need to figure out where these guys intersect. So let's just do this all, by hand. If we go, let's go ahead firstly and find the limits of integration, because we haven't been given any vertical lines. So we need to solve the nonlinear system of equations. So when we do this, we can call this, we'll do this one in blue. We can do this one in green. This second one in green. We'll get x squared is equal to 1 plus x squared over 2. So when we solve that, and if we get everything on the left side, we'll have positive 1/2 x squared, right? Because 1 minus a half is positive a half, is equal to, actually let's just solve it this way, is equal to 1. Multiplying both sides by 2, we'll get x squared is equal to 2. And then we end up getting the square root of x squared equals plus or minus the square root of 2. So x is plus or minus root 2. Good so far? So now let's take a look at the picture of the graph. So number 2, we're going to sketch the graph within those limits. We don't need, root 2, right, is approximately 1.4-ish, right? Plus or minus. So here, if we sketch our graph, both of the graphs, we just need a kind of a small you can just do it between -2 and 2. And when we figure out, we will have for x squared, right? When we graph this guy, we know we'll have an ordered pair at 0, 0, and then at, let's go here to 2, -2, and we'll have an ordered pair at negative root 2, 2, and positive root 2, 2. Okay, so we'll have this guy and this guy. I'm making it 2. Let's do 1, 1 as well. -1, 1, and then this guy to kind of get our, and this should be a little more over. Trying to get it really good so that it'll be easy to see the graph. Okay, so here we go. We're here and here for this guy. All right, so now the green graph, and so this is y equals x squared. Now the green graph is going to be at 0, do you see it will be, when x is 0, you'll have an output of 1. And when x is root 2, you'll have an output of 2 as well, right? And so what's going to happen is, if we go a little bit further, it's going to be wider, so it's going to end up going more out here. Much wider than the other one. The other one, if you continued on, you'd be going at a steeper rate. Okay, so our region of interest, this one's nice because we don't have to split the integral at all. And so we just have this single region that we're interested in, and it's right here. So which graph is on top? Good, the green graph, y is 1 plus x squared over 2, and the blue graph, y is x squared, is on the bottom. So now, when we find the area, we'll have area equals the integral from, and let's think about this. Here's a trick we can use. You can either figure out the area of the integral between negative root 2 to root 2, and then do your whole subtracting of it. So remember, you would have 1 plus x squared over 2 minus x squared, and that would all be with respect to x. But do you see that they're both symmetric about the y-axis, right? If you folded on them, they'd fold on each other. So what we can do is we can say, hey, I'm going to double this integral and evaluate it. Remember how easy it is when 0 is a limit of integration? So we're going to go double it and then just evaluate it from 0 to root 2. Either one will work. You'll get the same answer. And that, of course, was... Actually, let me go vertically. So the area would be 2 times the integral from 0 to root 2. And I'm going to simplify this. So we're going to end up with 1 minus 1/2 x squared dx. So our area will be 2 times x minus 1/2 x cubed over 3 from x is 0 to x is root 2. That's going to give us, let's simplify it a bit, our area will be 2 times x minus 1/6 x cubed from x is 0 to x is root 2. So we have the area is 2 times. So we'll have root 2 minus 1/6 root 2 cubed. Now if we factor out a root 2, we'll get 2 root 2 times 1 minus 1/6 times root 2 squared, which will give us 2 root 2 times 1 minus 4/6 times 2, because root 2 times root 2 is 2. And continuing, we'll have the area is 2 times root 2, and 2/6 is 1/3, so 1 minus 1/3 is 2/3. So at the end of the day, we will get 4 root 2 over 3 square units. And you're all done. So let's check this third example out. You're finding the area between the graphs x is y squared minus 2 and y is x. Well, so far all we've learned how to do is deal with functions of x, right? So here we'd be considering something a little bit different. We'd be looking at this one. We can write as y squared, sorry about that, y squared is equal to x plus 2. And when you have root y squared, you'd get plus or minus x plus 2. So y, and that, I'm sorry, that's in a radical. So y would be plus or minus root x plus 2. And y equals x is good to go. Now, when is the sign going to change? When is the sign going to change for the first one? Okay. All right, so let's just take a look at first the positive root x plus 2 And then we'll look at the negative root x plus 2. So first we'd be letting positive root x plus 2 equal to x. Squaring both sides, we would get x plus 2 is equal to x squared. We'd have 0 is x squared minus x minus 2. And that factors as 0 equals x minus 2 times x plus 1. So we would get x is equal to, good, negative 1 and 2 is where they will end up intersecting. Now I think we're going to be good to go, because if you notice, if we did the negative, I mean, this could really be plus or minus. Do you see that? Because what'll happen is you'd have your plus or minus and you'd be squaring it. So it doesn't matter what sign you had. So we have our intersection points. So now let's check out what we have. So x is going from negative 1 to 2. So we definitely need a sketch here. So we'll do our sketch. And I think the y values are going to be fairly low. So our x values are, we're going to have negative 1 to 2. And then we'll call this 1 and 2, negative 1, and negative 2. So what we have going on firstly is going to be, we have for x equal to negative 1, y will be plus or minus 1. Do you see that? So for our, so you can plug them into either graph, right? But you need to make sure you get your plus or minus from the second. So let's take a look. So if I do this one in blue and this one in green, what we'll have is y equal to plus or minus root x plus 2. When I plug in negative 1, I'll get an output of plus or minus 1. So I'll have negative 1, 1. And when we input 2, we'll get an output of 2, plus or minus 2. And let's check out what happens when we input negative 2. Good, we'll have an output of 0. So we end up with one of those sideways parabolas for this guy. It's a little squirmy. Let's see if I can get that better. Something like that. And then the graph of y equals x, of course, will just look like this. So we'll have an ordered pair here, ordered pair at 1, 1, and an ordered pair at 2, 2. We'll have this 2, 2, something like this. Okay? So our region changes a little bit, right? So if what we're doing, this is, sorry, 0, 0 is also. Okay, so what's going to happen is this region kind of gets chopped chopped up, because remember that this part here is our y is negative root x plus 2, right? And the above part is y is positive root x plus 2. So what ends up happening in actuality, our limits of integration, right, are going to go from x equals negative 1 to x equals 2. So what we have to figure out here is how to kind of chop this up so we get the entire area, okay? So it's going to look, it'll be an interesting graph, all right? So this is what will happen, which, as you can see, you know, is not going to be the whole region, because you're missing that other piece at the left part. So we're going to need to figure out two of them. We're going to need to figure out this region, this pink purple region, and then the blue region. So let's see what we got going on. So if we call this region 1 and we call this region 2, our overall area is going to be equal to region 1 plus region 2, right? So region 1, do you see it's symmetric, right? So let's take a look at this. We can either double that top part, or we can take a look at your rectangle, right? So the rectangle at any given time for region 1 is going to be root x plus 2 minus negative root x plus 2, right? This height of this rectangle, right? Height 1, we'll call it. So height 1 is really 2 root x plus 2. Now height 2 is, at any given time, is going to be, call this height 2. That's going to be the positive side of the parabola, the conic of root x plus 2, and then minus x, minus the graph of the line. So here we can find region 1 by taking the integral from negative 2 to 1 of 2 root x plus 2 with respect to x. And then we might as well go ahead and finish that out. So region 1 ends up being, if you do u is x plus 2, du would be dx. So I'm just going to do this using pattern recognition. So dc will get 2 times x plus 2 to the 3 halves over 3 halves, evaluated from x is negative 2, to x is negative 1. So region 1 will be 4/3 times x plus 2 to the 3 halves from x is negative 2 to x is negative 1, which will give us 4/3 times the upper limit of negative 1 will just give us 1 to the 3 halves, and then minus negative 2 plus 2 is 0, so you just have 0 to the 3 halves. So region 1 is 4/3 square units Now, you will have, for region 2, that'll look more normal, right? So you'll have the integral going from -1 to 2 of root x plus 2 minus x dx, which will give us, let's see, 2/3 times x plus 2 to the 3/2 minus 1/2 x squared, and that's all evaluated from x is -1 to x is 2. So R2 will be 2/3 times 4 to the 3/2 minus 1/2 times 4, working it out a bit. It's our upper limit minus our lower limit, 1 to the 3/2, and then we'll have minus 1/2 times 1, because we're squaring the -1 out of there. And so this will give us, R2 is, we'll have 2/3, square root of 4 is 2, and if I cube that, I'll get an 8. So 2/3 times 8 is 16/3 minus 2 minus 2/3, and minus a minus is a plus 1/2. So R2 will be 14/3 minus, I'll say 4/2 plus 1/2. So R2 is 14/3 minus 3/2. For R2, we'll have 28/6 minus 9/6, and we'll get region 2 is 19/6 square units. So now, recalling that our overall area was equal to region 1 plus region 2, we'll have the area is equal to 4/3 plus 19/6, which gives us 8/6 plus 19/6, which gives us our area is 27/6, and 3 divides both, so the area is 9/2 square units. Now that one was a bit tricky, wasn't it? I mean, we had to kind of think about all these things, and there is an easier way. If you think about making this into a function of y, right? Instead of thinking of topmost minus bottommost, we think about rightmost minus leftmost. Okay, rightmost minus leftmost. So in general, if you had, let's take this problem that we just had. Well, no, let's do a general one. Okay, so let's say you had some function of y. Let's say it looked like this. So this was your function of y. And suppose you had another function of y that looked like this. So this would be g of y. And, this is x and this is y. So what happens is, instead of topmost minus bottommost, we're looking at rightmost minus leftmost. So because our rectangle is now going to be going this way, okay? And so you end up with, instead of a change in x, you end up with the base is the change in y. And this height measure is going to be rightmost minus leftmost. So in this case, do you see it would be our g of y minus f of y to get a positive number, right? We want a positive number. So in general, for functions of y, there's a couple things that change, right? So you have different limits of integration because they're y values. So usually we call this c and d. So for functions of y, the area in general goes from c to d. There might be changes, if they switch or whatnot, but from the integral from c to d of the rightmost minus the leftmost graphs, and it's with respect to y. So let's revisit our other graph, right, that we did here. And notice how we did the rectangles and had to do all that configuring. Well, let's do another sketch of this bad boy and take a look at how we could solve this problem. Instead of keeping this as y equals x, we would say x equals y. And our graph, I'll just do it on top. Our graph is going to look like, it'll be the same graph, but the pictures will be a little different. So 1, 2, 1, 2, -1, -2, and then 1, 2, 3, 4, -1, -2. Okay, so if you recall, the blue graph went something like this, and then our green graph went something like this. Oops. And our region is this guy. Now, the trick to this one is going to be, we're keeping everything as a function of y. So when you solve for your limits of integration, and consider your rectangles, basically what happens is you're considering this rectangle here, okay? So remember, we're looking at a change in y, so your limits are going to be about y. So if you do the same thing, find limits of integration, it's a lot simpler because there's not going to be any radicals. So what you'll have is you'll equate each of them, right? So you'll say, okay, y squared minus 2 equals x. I'm sorry, not x, but y. And then when you solve them, you'll get y squared minus y minus 2 is 0. And then you'll have that factors as y minus 2 times y plus 1 is 0. and you end up getting y is 2 and y is negative 1. So what happens is you now have these limits here where you're going from here up to here. Whoops. All right. This went a little bit lower. Actually, my 2 was a little high. I think it'd be easier to fix that. Okay. This is our 2. So that's our 2, right? So our that's what our limits are going from. Instead of vertically, they're horizontally going. So what we have then is we have our everything, do you see, is comprised between these. We don't have to chop anything up because all of the graph is accounted for between that. When we go to find the area, right? So our area will be equal to the integral from y is negative 1 to y is 2 of, now remember our rightmost graph is the graph x equals y, right? So we use the y. And then our leftmost graph is y squared minus 2. And remember, this is all with respect to y. We will get y squared over 2 minus y cubed over 3 plus 2y, from y is negative 1 to y is 2. So our area will be I think we'll get 4 over 2 is 2 minus 8/3 plus 2 times 2 is 4. I guess we don't need this bracket. And then minus, so negative 1 squared is 1, so we'll get a half minus negative 1/3. And then minus 2. So that's going to give us our area as 2 plus 4 is 6, and then we'll have minus 8/3 minus 1/2, and we'll still have a negative 1/3, and then we'll have a positive 2. So we'll have an area of, let's see, 6 plus 2 is 8. And then negative 8/3 minus 1/3 is negative 9/3, which is minus 3. And then minus 1/2. So our area will be equal to 8 minus 3 is 5. And 5 is the same as 10/2, and then minus 1/2. So our area is, lo and behold, 9/2 square units, which is much easier, I think, than doing it as a function of x. Okay? Last problem. We're going to find the area between these graphs. Again, we have f of y. So let's check it out. Let's just do them as functions of y. Here we go. 1, we can find, we weren't given any limits, so find limits of integration. And so if this one is this will be our blue one, and this will be our green one. And remember, you can think of this as x equals y minus 1 as well, if that helps. Actually, this should have been a, sorry, here's a typo, it should have been a g of y. Here we go, we have our blue graph, we set the graphs equal to each other, so we have root y plus 1 is equal to y minus 1. Squaring both sides, we have y plus 1 is equal to y squared minus 2y plus 1. And then we'll have 0 is y squared minus 3y, and the 1's will zero out. Factoring, we'll have y times y minus 3. So our limits of integration will be y is 0 or y is 3. So doing our, let's see how much room we have to work, doing our sketch, right? So we're going from y is 0 to y is 3. So I think our rightmost output is going to be 2. So we don't have to make it very big. So 1, 2, negative 1, negative 2. And we already know that y is going from 0 to 3. So 1, 2, 3. Okay, so now looking at our blue graph, which is f of y is equal to the square root of y plus 1. If we know that we'll have, when we input in f at 0, we get root 1, which is 1. We also know that if we put in f at 3, let's see what we get. So that'd be root 3 plus 1. So that would be 2. So remember, these are x values. So this gives us the ordered pair 1, 0. So be careful about that. And this one gives us the ordered pair 2, 3, because those are functions of y. 1, 0 is here. 2, 3 is here. Okay, so far? Might want to find some other ordered pairs to complete the graph, just to get a visual. At negative 1, do you see it'll be 0? And that gave us the ordered pair 0, negative 1, which would be here, about here. And so look what this looks like. Kind of cool, huh? Bet you never thought about it that way. Let's take a look at the other one. Your other one is g at y was equal to y minus 1. And so this is going to be a line. So if we do g at 0, we'll get negative 1, which gives us the ordered pair negative 1, 0. Which is here. And then g at 3 will give us 3 minus 1, which is 2. So remember, that's going to be 2, 3. And that's here, that intersection point. And now we've got now on this one, really we should have included, I mean, it might be accounted for with the domain, but we should also include another bound, I think. I think we should include a bound of x also equal to 0, so that it closes. Otherwise, you wouldn't be subtracting out all the area, since there's domain restrictions on root y plus 1. Okay, so that makes our region like this. And so our area will be equal to, now remember, you're going rightmost to leftmost. So with this one, let's see what's going to happen. Do you see that the graph changes here, right? When you're thinking horizontally. So we're going to be splitting this graph up. So what we'll have is, on one side of this, actually let me do that one in a different color. Or I can do this in a different color. So here, this is your rectangle for that one. Oh, that worked. So this is your rectangle for this one. And then you'll have a different leftmost graph down here. So when you make your little rectangle, it's going to be changing. And so we're going to have to split these integrals, and at this part right here, when x is 0, and remember this ordered pair right here is going to be zero, 1. Okay, so far? So, here we go. This area is equal to the integral from. So from y equal to -1 to y equal to 1, we're going to have our rightmost graph is, well, our rightmost graph is always going to be the blue graph, which is root y plus 1. Our leftmost graph is going to be the line x is 0. Okay, so that would be, we had done that one in red, so -0. And this is with respect to y. And then we'll add to that the area of the upper region, and that's going from y is 1 to y is 2. The rightmost region is still root y plus 2, and the leftmost region is now that line, which was y minus 1. And it's with respect to y. So we will have the area is two-thirds y plus 1 to the 3/2, and that's evaluated from y equals -1 to y equals 1, plus two-thirds y plus 2. Oh, is it y plus 2? No, it's y plus 1. So y plus 1 to the 3/2, and then minus, I'm just going to look at this as a quantity, y minus 1 squared. I'm going to make sure I didn't mistake that radical. Okay, good. All right, so then we'll have y minus 1 squared over 2, and these are from y equals 1 to y equals 2. Continuing, we will have area is, this will be 2/3 times, the first one when we put y in, we'll have 2 to the 3/2 That's not very neat. So we'll have 2 to the 3 halves, and then do you see the second one was 0? -1 plus 1 is 0. And then we'll have 2/3 times 3 to the 3 halves minus 2 minus 1 is 1, so you'd get 1/2. And then minus 2/3 times 2 to the 3 halves minus 1/2. Continuing, we have 2/3 times 2√2, that's 2 to the 3 halves, plus 2/3 times 3√3 minus 1/2 minus 2/3 times 2√2, and then plus 1/2. So let's see what we have. Our area will be equal to, let's see, this and this 0 out, and this 0 out. So all we're left with is 2√3 square units. Okay, so hope you enjoyed the show. Go have a glass of wine or something. I know I sure need one. And have a fabulous weekend. Bye.